Hi, today we're going to revise and slightly extend indices for A level. So to start this off, I'd like you to think about what the question marks are in each of these situations here. So the first one, question mark is going to be 7, so it's 2 to the 7. Here, it's 3 to the 5. Here, there's lots of possibilities. Actually, you just have to make sure that they add to give 12. So you might have gone for 1 and 11, or 2 and 10, 6 and 6. You could even do some like cheeky ones like 0.5 and 11.5 as long as they add to 12. And this one here, similarly, there's like an infinite number of solutions here. You just got to basically have this one minus this one is this one. So we could maybe have 6, 2, 4, and all sorts like that. And my question is, like, what rules have we used here for indices? And the answer is that we've basically used x to the m times x to the n is x to the m plus n, and x to the m divided by x to the n is x to the m minus n. How about these questions here? So this first one is going to be 2 to the 6. I just put a little 6 there. Right, the second one is actually going to be 8. Couple ways to think about it. You might write it like 2 squared and then raise it to the power 4, and then use a similar thing to the first one, 2 to the 8. Or you might have written it as 2 to the 4 times 2 to the 4 and then added the powers. So two ways to do that second one. Be aware of both. And this last one, just any combination of numbers at times to give 12. So it could be 2 and 6, 3 and 4, half and 24, and so on. And the key rules that we've been using are x to the m all to the power n is x to the m n. Two more. If we have, say, xy to the n, then that's going to be x to the n, y to the n. That's the sort of special case I used here. And although there's no question on it, the same goes for division. If I got x divided by y all to the n, then it's x to the n divided by y to the n. And my only question left is, how can we prove these rules? These are sort of rules we learn earlier on in the school normally, and you may have been shown the proofs for them. But if not, or can you remember them, or can you think about how we might go ahead and prove them? Well, I'm just going to talk. I'm not going to sort of prove every single one, but let's say I'm just going to give some. I mean, and this is actually really the proof. You sort of just give some inspiration to it. So I'm gonna do this one with numbers to start with. So if I had x to the 3 times x to the 4, you can remember that I've got x times x times x. That is x to the 3, and then I'm timesing by x times x times x times x. That's x to the 4. And if I count how many I've got 7. So I can see that it's x to the 7. And I could extend this. I could say if I've got x to the m times x to the n, well, the proof is very similar, but this time I've just got dot dot dot. I've got m lots of x. And then I'm going to times by x times dot 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 times x. And here there are n lots. And it kind of just falls out then that if I've got m lots and n lots, then I'm going to have x to the m plus x to the power of m plus n overall. Similar sort of argument goes for division. You might want to think about how you can show that. I think I'll talk about this one here. So x to the mn. This is quite a nice one, because x to the m to the n is going to be x to the m times x to the m times dot 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 times x to the m. I've got n lots of it. And so if I was to add them together, then I would get x to the m plus m plus dot 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 plus m, and again I've got n lots of this. I'm not going to write that in because it'll make it a bit more confusing, but I've got n lots of m, so it's n times m or m times n. I could leave it as their equivalent. So that's kind of a proof of that. The only thing I'd say is that I've only really proven it when it only kind of makes sense when I've got nice numbers like 3 and 4, whereas the rules do work for negatives and 0.5s and so on. So it's not really a proper proof, but I did want to just remind you about these. These are where the rules kind of come from. We can do it for whole numbers, nice whole numbers. We can then sort of, we see that the rules actually do work for other numbers as well, but we're kind of like haven't really proven it for that. So using these rules, I want you to have a go at these questions here. Well, the first one, actually, I haven't spoken about this so far, but I just thought I'd throw it in, and I'll bring it in a bit later on, but it is going to be 1 over 11 squared. When you have a negative, you flip it around like this. It's actually 1 over 11 squared, and then you can do 11 squared and we get 1 over 121. That's my answer. This one here, 2 to the minus 3 divided by 3 to the minus 2. These don't have the same base, so I don't like do anything with the powers. That's the first thing to notice. So it becomes 1 over 2 to the cube. I'll probably write it as fractions, divided by 1 over 3 squared. That's going to be 1 over 8 divided by 1 over 9, which is actually 1 over 8 times 9 over 1. I change it to a times and flip it around. So I'm going to get 9 over 8. Probably the best way of doing that one. You could arguably have, you could have changed it to times 3 squared right from the start if you kind of recognize that if you divide them by negative power, it's the same as times them by the positive power. This next one is x to the minus 3. I just add the powers. Okay, but they're negative, so they go in the negative direction. Here, I've actually got, it's like I've got 1 over x all to the minus 2. You end up sort of flipping it around. Actually, it makes more sense to just times the powers. You get to x squared. You can, like I started out with this, but it's just confusing. It would technically then be 1 over x squared, which is 1 over x squared, and you would, if you do 1 over x squared, you'd get x squared. But yeah, you don't really need that, but it's kind of good to see it. Here I'm using this a to the n, b to the n one, so it's going to be p to the 3 squared. So that's going to become p to the 6, and q to the minus 1, then squared is going to be q to the minus 2. Substituting in a number here, 4 times 5 to the minus 2, which is going to be 4 times 1 over 5 squared, which is 4 times 1 over 25, or 4 over 25. Next one, I've got a few more here for you to look at. I'm going to get 4a squared b times 3 squared. Remember, I square that, 9, and then I square the a, and I square the b to the minus 1, so it becomes like so. And now I can think about dealing with the numbers. It's going to be 36. Deal with them separately. 4 times 9. A squared times a squared is a to the 4. And b times b to the minus 2. Don't forget this is b to the 1. To add the powers, I'm going to get b to the minus 1. Of course, I could have written it as b over b squared if I wanted to, and got 1 over b and converted back to b to the minus 1. But these like indices rules means you can take shortcuts. Similarly here, it's best to just basically cancel things off. I can cancel that a with the squared, and I can cancel that b with the cube to leave the 2. I can do 20 divided by 4 is 5, so it's going to be 5a over b. Slightly trickier one here. Probably the best thing to do is I'm going to get rid of the brackets first of all, write it like this, and then change that to a times. and flip the whole fraction round. Just easier to deal with. This is looking better. And then let's simplify each term like separately. So I'll get rid of this L and get rid of that squared. So it's going to become, I know I've got a t to the minus 2 on top, but let's just go with that. And then this L and this L to the minus 3, that's more difficult to sort of cancel out. So I might leave it for the moment. I'm just going to write it out again like this. There is more than one way of doing this. Okay, then I'm going to multiply the fractions out, I think. So I'm going to get m t to the minus 2 times m, so I'm going to get an m squared, and then L to the minus 3 divided by L squared t to the minus 1. This is a bit easy to deal with because I can see that I've got my m squared, I've got L to the minus 3, then I'm dividing by L squared, so actually minus 2 from the power, so I'm going to get L to the minus 5. And t to the minus 2 divided by t to the minus 1, that's going to be double negative, minus 2 minus minus 1, I'm going to get left with t to the minus 1. I could, if I wanted to, write this as m squared over L to the 5t. That would be two different ways of writing that same answer down. And the last one is actually 1. But why is that? You might have been taught that, always raise to the power 0 and get 1, but that's an interesting question, I think. So we're going to move on. You get practice a little bit more of that in a bit, but this is another key part of indices. Can you rewrite these calculations in powers of 2? So when I say powers of 2, I mean things like 2 to the power 1 is 2, 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16. So if I said to you write 16 as a power of 2, you would write 2 to the 4. So this calculation here, I'm hoping you've paused and given this a go. It's going to be 2 to the 4 divided by 2 to the 3 equals 2 to the 1. We see that it works. It's just writing it in powers of 2. Here, I get 2 to the 4 times 2 to the minus 1 equals 2 to the 3. Again, the rule works. This is what I'm trying to get out of here. This is why a half is 2 to the minus 1, because it works here. Half of 16 is 8, and it works here. If we use our rules of powers, then it's okay as well. So if you didn't get that 11 to the minus 2 before, it follows in the same kind of way. Here, we've got 2 to the 3 times, okay, this is actually 2 squared, so it's 1 over 2 squared, so it's 2 to the minus 2. Again, this works. 3 plus minus 2 is 1. So yeah, that again helps us understand that, yes, 2 to the minus 2 is the same as 1 over 4. And finally, this one, right, this is just testing if you can remember this. It's 2 to the half times 2 to the half is 2 to the 1. And that works, doesn't it? Half plus a half is 1 if we use the rules of powers. And this is, again, in like kind of a semi-proof, or at least evidence, why root 2 is the same as 2 to the power of a half. So what rules come from that? Well, really, the rule I'm trying to get out is x to the minus n is 1 over x to the n. Really important. And also x to the 1 over n is actually the nth root of n. So if it's a half, it's the square root. If it's a third, it's the cube root, and so on. I might have preempted some of these here with that kind of thing. I actually did it here. This one would be 2 to the third times 2 to the third times 2 to the third equals 2 to the 1. If we times the cube root of 2 by itself 3 times, yes, we're going to get back to 2. And we see the rule of indices works here. We add the powers and we get 1. Here we've got 2 cubed times 2 squared equals 2 to the 5. That's nothing really new. Here I've got 2 to the 4 divided by 2 to the minus 2. And again, we see we do 4 minus minus 2. That's going to give us 2 to the 6. And finally, this one here is actually 2 cubed divided by 2 cubed equals 2 to the 0. And actually, this is kind of what I was getting at before with, why is this true? This is sort of evidence or semi-proof towards that. We can see that when you divide it, you're going to get 2 to the 3 minus 3, and that's going to give us 2 to the 0. So that's why 2 to the 0 makes sense, because it's sort of like a number divided by itself. Like you can do it with another one. So 7 divided by 7 is equal to 1, but 7 is actually 7 to the 1 divided by 7 to the 1, which is 7 to the 1 minus 1 if you use the rules of indices, so it's 7 to the 0. That's what I'm trying to show you. Why is something to the power of 0 equal to 1? A few more to try then. Let's just finish things off. This is probably bringing it into the realms of A-level. I mean, some of this stuff, yeah, there's a lot of it. It's on GCSE, maybe you do get ones like so. What I've tried to do today really is just recap that and just test you on it. Bringing in a few extra ones here, bringing in like the reasons why again, and also being able to write numbers of powers of 2 or any other number like powers of 3 in theory, in fact, and so on. Just to finish off then, can you have a go at these slightly trickier questions? Okay, so how do we do this, especially without a calculator? Well, we need to try and write it as powers of 2. So we've got 2 to the 40, and then 4 is actually 2 squared. So I can write it as 2 squared to the 30. 8 is actually 2 cubed, so I can write it as 2 cubed to the 20. And then 16 is 2 to the 4, so it's 2 to the 4 all to the 10. Where does that leave us? It leaves us with 2 to the 40, and then I can use my rules of indices from before. 2 to the 60, 2 to the 60 again. In fact, 4 to the 30 is the same as 8 to the 20. And then 2 to the 40, because 2 to the 40 is actually the same as 16 to the 10. I can add these up. I'm going to get 2 to the power of 200. Express 7 root 7 in the form 7 to the power 7. How do we do this? Well, I've got 7 to the power 1 times 7 to the power of a half from before. And so we can add the powers. We're going to get 7 to the 1.5, which we normally write as an improper fraction, 7 to the 3 over 2. Evaluate means like work out this. I think actually this should probably be simplify. So I'm going to get 3y cubed times 10 squared, which is 100, times y to the 5 squared, which is y to the 10, divided by 5y to the 4. Need to simplify this further, so I can add, I'm going to get y to the 13, but then I'm going to minus 4, so I'm going to get y to the 9. And I've got 100 divided by 5, that's going to be 20. 20 times 3 is going to be 60, so I think that's the answer. This next one, 2 ways to do it. Okay, method 1 is you could expand it and write it as 25 to the minus a half, x squared to the minus a half. And then deal with these separately. This is going to become 1 over 25 to the half. Don't forget to deal with how you deal with the negative. And then this one's a bit easy to deal with. In fact, it's just going to be x to the minus 1. Now, this becomes 1 over the square root of 25, x to the minus 1. So it's 1 over 5, x to the minus 1. It does say write it as a fraction, so really I should finish it off and write it as 1 over 5x, because x to the minus 1 is 1 over x, and then I can bring them together. Quite possibly a quicker way of doing it is, maybe I should have done that, is you could literally write it as 1 over 25x squared to the half from the start. And then you might say it's actually a bit easier to deal with, because it's going to be 25 to the half, and then just x by itself, which again goes to that. So yeah, fair enough. Maybe if I hadn't have split it up, I'd just gone straight to it, would have been quicker. And finally, this one here. Okay, Again, just remember your powers of 2, so this is going to become 4 is 2 squared, and then it's the power third. And this is already written as a power of 2, but we're trying to combine it into a single thing, so we need to think about that. But actually, this is great because actually I've got 2 to the power of 2/3 from here. Now we're actually going to do, we're going to recap fractional powers like this next lesson when you have 2 to the 2/3 or 4 to the 8 to the 2/3. Today we've mostly just dealt with unitary fractions, 1/3, 1/4, 1/2, and so on. But we can deal with this. I'm not being asked to. We're still leaving it as the power of 2, so it's okay. Now actually I've got 5 lots of 2 2/3 and 3 lots of 2 2/3, so it's going to become 8 lots of 2 2/3. That's the key thing to remember this question, because I can't write 5 as a power of 2 very easily, or 3 as a power of 2, but now I've got 8, I can. It's going to be 2 cubed times 2/3, which I can either write as 2 power of 3 2/3. This is always a bit confusing because you've got like a power and a fraction. You can easily sort of misread that. So maybe best to leave it as an improper fraction. 3 is going to be 9/3. Add the 2/3, we're going to get 11/3. So that is it as a power of 2. Brilliant. I hope that makes sense. I hope you've done some good practice. Try some more questions out and make sure you're happy with this introduction to indices in A-level.